have a battery which has particles, and you want to, you want to exchange particle number for, or angular momentum. You could also put a, minus beta j. So you have some angular momentum, and you have an angular momentum battery, and you can trade off angular momentum for energy, and you use this generalized Gibbs state, as an exchange rate, and all these things are basically exchange rates. These chemical potentials are exchange rates, and they tell you what the conversion rate is for one resource to another. So I don't know what to call this state in a generalized resource theory, but Charlie's good at naming things.
Well, I think bank is a good name because you
bank is a good name.
Yeah, well, you give it one kind of currency and give it another one. I mean, they defeat.
Yeah.
That's like the anarchist version of the bank where it doesn't charge you.
Okay, we call it the anarchist bank. I'm okay with the anarchist bank. Okay.
So I guess there's some result that says that if you just create something that is the intersection of the two free states sets and allow the union of the states and the intersection of the operation, this is not going to be a resource theory?
Well, okay, so let me get into that. There's different kinds of resource theories. I just want to give a simple example first, and then you can think about what. So now we want to generalize this and think, and the first thing you notice is that the set of so what we were calling the set of free states, we should not call the set of free states, because notice that we shouldn't be allowed these for free or these for free, because purity, the energy free state, which was worthless for the theory of energy, is actually a very good state for the purity theory, and the maximally mixed state, which was useless in the state in the theory of purity, is actually a pretty good state for the energy resource theory. So free states if you consider the double resource theory, the free states are of one resource theory cannot be the free states of the combined theory.
So first of all, you could call it the Bennett state without changing notation. but a question about it. So this seems a little abstract.
Okay.
But it sounds like you're really aiming at a more practical concept, like you have an actual bath or a thing that you can really use in this way. And I just want to check in about that.
I thought it the opposite way. I thought this was very concrete, because I was talking about thermodynamics, and I'm going to make it more abstract by talking about generalized resource theories.
So,
but where I don't even tell you what the resource is, I just tell you.
So we're never
I have
in one particularly chosen state out in the world.
No. So
in that sense, it's an idealized case or something.
Well, okay, so
I just want to.
Right. So okay, good. I think I'm not sure exactly what you asked, but here this is the open system approach, where I have a system and I'm putting it in contact with a bath.
So this is like the bath.
This is like the bath.
Okay,
yes.
that's all.
I will. So when we get to I have to, right? When we get to the black holes, then now we need to go to closed systems, and we need to again. So what I found with these two projects is I've chucked everything that I thought we badly defined initially, and now we have to throw everything out. So when we go to closed systems again, we need to rethink how we talk about thermodynamics a bit. Well, not really, but you get some interesting things happening. Okay, so good. So I think we kind of think of resource theories as dividing into double resource theories or triple or whatever as coming in three flavors. You can imagine that your set of free states do this. So there's resource theory 1 and resource theory 2. And one's inside the other. The set of free states are inside the other. For example, for the set of purity, it would be the maximally mixed state. That's right here. And then the set of coherence, it's all states which are diagonal on a certain basis. And that's these states here. So that one's inside the other. Can't say much about this. I mean, we can say some things, but they're not so interesting. Then there's this overlapping case. For example, so the three states overlap. For example, here separable states. Here are symmetric states, which are symmetric with respect to some supersymmetry or some symmetry, and so they intersect, but they don't always. So that's an example of that kind of a double resource theory. And then the ones that are, I think, where you get this first law are like these kind. So the set of free states are not overlapping. And our resource theories that we take, the double resource theory or the triple resource theory that we take, if we have a class of operations for each resource theory, we take the intersection of all the, so our multiple resource theory is just equal to the intersection of all the things you can do, right? So you have many restrictions, basically. So your class of operations becomes smaller, which make you think you're not going to be able to do very much, but then because you'll get the bank state, you'll be able to do stuff. Okay. So an example of this is here's the energy free state or fixed state. Now we're going to call them, and here's the purity free state. And the thing to see here is that that we can no longer give these for free. So we're not going to call them free states. We're going to call them fixed states. They are, if you are given one of these states, and the class of operations will keep you within that set. But we don't give them for free because it's very clear that anything from this set is a resource for something from this set, and anything from this set is a resource for the resource theory, which has this set as the set of free states.
Jonathan, did you say what is this in the intersection case?
Oh, here?
Yeah.
No, so here is S1.
Yeah.
So for here's.
So what's the union is?
You mean the union of the two fixed sets?
Okay, you don't want to build a resource theory for the for C mod. Are you building a resource theory for C mod?
C mod.
The multiple.
Oh, the multiple. Yeah. So I said there's three different, or at least three different ways.
Let me rephrase the question.
Yeah.
Are you going to build now a resource theory for C multiple?
Yes.
And thereby also define an S?
Yes.
Okay, so what is S?
So I don't want to do it. So in this case, it depends. So for example, if I'm allowed mixing, so I guess it's like any convex. So it'll clearly include these things here, right? Because if I mix two states, then and I can't get out, then.
So it has to include at least S1 and S2, but potentially more.
Yes.
Okay.
Yeah. But I guess the thing that we've learned is we should no longer think of free states anymore. Okay, so here is the one I'm going to be interested in because this is where we get our first law. You have two distinct sets of states which were fixed under. So this was fixed under resource under, say, C1. So this was the fixed state which you could not get out of when you had resource theory 1. These were the set of fixed states when you could not get out of resource. That you could not get out of when you were operating under resource theory 2. And now you're going to take the intersection of those maps and you want to ask what is that resource theory. Okay?
Sorry, but the set of free states is like a new thing you have to provide.
No. So previously each resource theory we used to talk about the free states, and we used to talk about the relative entropy distance to those free states.
Yeah.
Okay, so let's call this F1 is the relative entropy distance to those free states, and F2 is the monotone for resource theory 2. It's the relative entropy distance to those things. And now we're no longer going to give those for free. We're just going to say we should have called them the fixed set. Those were the set of states which, if you act a map from C1, you cannot get out of this set of states, and likewise, if you act a map from C2, you cannot get out of this set. So they're now, let's call these the fixed sets.
Okay, but the new double resource theory, will it have free state?
So it will have the bank state, which is going to be like, so here, so think again of thermodynamics. You have, this was the free state for the energy resource theory, this was the free state for the purity resource theory, and then we introduced the thermal state, and we saw that we could convert one thing into another. We can convert energy into purity and purity into energy, and we can imagine that we have a purity battery and an energy battery. So you have an energy battery, which is like a ladder with a Hamiltonian, say evenly spaced or whatever, continuous, and you can use the energy battery to do Landau erasure and create some purity. We can also imagine you have a purity battery, which is a bunch of some number of pure states, and you can use some number of mixed states, and you can use that purity battery and convert it to energy or add it into a state. So here in thermodynamics, we like to think of it that we have a battery for energy and a battery for purity, and then we have our state of interest, say rho, and now we can do some state transformation where we invest some energy and we invest some entropy or some purity to get a new state, sigma. So that's kind of a transformation you might do in the double resource theory, where you have a battery for resource theory 1, a battery for resource theory 2.
Where's the bank state?
So the bank state is in the background because the class of operations includes the bank state. So, yeah. Just like for thermodynamics. So thermodynamics is the bank state is just the Gibbs state. So you don't write the Gibbs state in, you just have it as a resource. You can attach the thermal states to, you could put your systems in contact with the thermal reservoir and do the transformation, and then you don't care what state the thermal reservoir is in. Yeah?
Sorry about that. Now, when you define C multiple, the way you did it there,
Yeah?
and let's say that you take sort of some kind of closure of the different S's, do they coincide?
Oh, I didn't say it takes a closure of the S. I just say
No.
I'm going to define it like this, and then I could then ask what the fixed set is.
Now, if you did this other definition you talked about earlier, where you start with S and from that you derive the corresponding C,
Mm-hmm.
does that hold here too?
We don't know.
What?
We don't know.
You don't know, but no counterexamples are known.
Sorry?
No counterexamples are known.
No.
There are no counterexamples that anyone has.
Counterexamples. I guess I'm not sure. So if you're talking like, can we prove a theorem like the Brandau-Gur theorem, I would say we don't know. And that seems difficult to prove, is what I would say. But it's an interesting question. But but what we do is we go to the result of Michał and I, where we just say, if I have a reversible theory, then the relative entropy distance is the unique monotone. So we have this theorem that says, in any resource, you define a general resource theory like this, and you say, if I have a reversible class of operations, then the relative entropy distance is the unique monotone. So we just use that. We say, let's look at theories which are reversible, and then we get a first law. So it's a generalization of that result. So I'll maybe just say what the result is, and then go to black holes. The result, so in thermodynamics, you have something like this. You have work 1, which is the resource in the first resource theory, plus work 2, which is the resource in the second resource theory. This goes on to multiple resource theories, is equal to some change in the bank monotone. Okay? And the bank monotone is just the relative entropy distance to the bank state. So in thermodynamics, this would be dF. It would be the change in the free energy, because that's the relative entropy distance of your state with the. So this is the bank monotone of rho. So you're changing the free energy of the bank. Of the state, sorry. And this is du minus dq. So this is like the first law in thermodynamics. So you have resource 1, which is energy, resource 2, which is heat in this case, and then the change in free energy is just the relative entropy distance of your state to the reservoir state, the bank state. Right? So this
sigma doesn't appear?
Sorry?
The sigma?
The sigma, so this is just, well, let's write it. This is f of Well, this is the relative entropy distance of, what I was calling E. So this is E, which is less, yeah, so this is E, so the relative entropy distance, that monotone there, E1, let's call it, of rho minus entropy, relative entropy distance, sigma. So that's the change. So the change in your relative entropy distance to your bank state, that's this what's happening here, which is for thermodynamics is the change in free energy, is equal to the change in relative entropy distance to this fixed state plus the change in relative entropy distance to this fixed state. So you basically have three different fixed states for different resource theories. The S1 for resource theory 1, S2 for resource theory 2, and then your bank state. And those three relative entropy distances give you a first law of which thermodynamics, the ordinary first law, is a special case.
And in each case, you will have to define what the bank state is, or is there a way to construct that from the...
Yeah, so there's a way to construct it, and in some sense, actually I should have an alpha here and a beta here. For each bank state, you get a different alpha and beta, and for thermodynamics, you know, this is just the one, and this is the temperature, the inverse temperature. So you, whichever, there's a whole equivalence classes of bank states, and each bank state